So that's one way we can think now of fully developed flow, is that there's no momentum change in the x direction, right? And that's all we were saying before when we said if I looked at the profile at an x naught and then I went down the pipe, I would have the exact same velocity profile. So that this whole process is just proving to you that would be the case because there's no change in momentum from this x to this x. It's not quite informative yet. What's really informative is this, right? Sum of the forces in the x direction equals 0. So you can also think of this now as I already assume that I have steady flow, steady being right, sum of the forces equals 0. So it's the same as solving for like something moving at a constant velocity, but it's fluid, so there's a couple more things we have to think about. So that 0 means that all the forces I can find have to equal 0. So let's remember what the control volume that we drew. I had a P, then plus a P, and then I had my shear force. Okay. So let's add forces. The way we add forces is we take pressures and we multiply them by areas. So count them up. Right? You have this minus remember, this 2 pi r delta x is just the surface area of this cylinder that we're drawing, right? And I have a shear, so if I want the total force in that x direction, it's the shear times the surface area. People forget where that one comes from. Okay, then, so if this is all equal to 0, right? Solve this around, throw the minus sign because the arrows are flipped the wrong way. Solve this, and we get our first big, giant, awesome equation. And I want to explain why this one's pretty important. Okay, for all the assumptions that we had for fully developed flow in a pipe, this dp dx equals to this relationship based on radius. Notice one key thing. This is for laminar and turbulent flows because I haven't made any assumption based on a speed or some type of flow like laminar. That's the next thing we're going to do. But this control volume approach allows us to say something about shear forces. So in turbulence, they get at a lot of shear forces or mean shear flow or shear flows. I'm not a turbulence expert, but this is why one thing they look at shear so much, because you can do this approach and you can get relationships based on the shear forces. Laminar, we get totally analytical solutions past this step. Okay. Again, if it was fully developed, this is actually equal to some constant value, right? We just actually call this thing K. And that's for the fully, so, right, this is true for all those 4 assumptions we made, so that's what we should go by. This radius is measured from the center line. Right? Right, that's from the center axis line. So let's keep going on this using this idea that for the fully developed flow, I knew that this pressure gradient was actually equal to some constant value. So I have K in the notes. Sometimes people call this, right, whatever it is, they'll call it a G, I think, to remind themselves that it represents the constant pressure gradient. I've seen that somewhere. Just beware, I'm calling it K. I think your book calls it a K2, but I'm not too worried about that. But this is the cool part. This is actually a really cool part that we can say things, right? So we'll just call it K, and you solve this and you get that sort of second big aha. It's this relationship that the stress is linearly proportional to the radius from the inside of the pipe. So that, that's a pretty cool thing, right? You can orient yourself with this picture in my head. Here's the radius, right? What this is telling you is what? So when this is 0, right, no shear. That means at the center line, we should have no shear forces. And then past that, it just gets bigger and bigger and bigger and bigger, right? When you have linear relationships, you should always just, in your head, and I draw this so many times in the notes, you realize, here is my R for the pipe. Here is shear. What's happening is it's just this line. This thing is the slope, which is like half the pressure gradient. So it would just continually go on, except that it ends at a certain point because this has a diameter. So this point right here is half the diameter of the radius, in which case that means that there is a maximum shear occurring in the pipe. Where is that maximum shear? It's at the wall. So in your pipe at the wall is the most shear force happening in the flow. That's pretty important, and you can say a lot of things. That's right. That's we're getting at. So that's what we care about, the interior of the pipe that will get us expressions like these friction factors. But just from the simple control volume you did, we can already derive that shear is linearly related to the radius from the inside of the pipe. I think that's pretty fascinating. Okay, next, let's introduce the flow being laminar.